probability distribution with binomial distributions here. So they've given us some information, and we have to kind of make sense of what does this all mean. Oops, that wasn't supposed to happen. Our formula here for the probability of success depending on the number of successful trials deals with a combination, and the combination starts with the number of trials and then the number of successful trials. So we should actually, or I should, we can kind of define what these stand for. So what the N is and what the X is in this case, and then again what the P and the Q are. So X is number of success, okay. N is number of trials. Now our P value is probability of success. And our N minus X is essentially telling you the probability of not being successful. So they've given us P, and P they stated as 0.2. So what that means in terms of a probability, usually percentages make a little more sense there. If we multiply that by 100, that gives us the idea of 20%. So what they're saying is whatever we're working on has a 20% success rate, okay? And we want to run it through 5 trials. And we want to find out, we want to build a table representing all 5 of those trials. So what that means to us, okay, so they have our probability here. P at X, X being the number of successes, well, we're going to start X at 0. So we're going to say, what's the probability of having absolutely no success if there's a 20% success rate? The number of trials is 5, okay, so we have 5, C. Our X in this case is 0. Our probability is 0.2 to the power of 0 because we're expecting no success rates. Okay, the probability of failure, which is our Q. Oh, I forgot to define that. Q is prob of failure. And really, it's just the opposite probability of what P is. P could be technically measuring failures, but it's the rest of what P is. So if P is 20%, Q must be 80%. So in terms of a relationship, P is equal to 1 minus Q, and 1 minus P is equal to Q. These are kind of, they have a relationship to each other because they have to add up to 1. P plus Q must equal 1, okay? And N minus X, well, in this case, that's going to give us to the power of 5. So we run through this here. Our combination of 5, C0, got a little calculator here. Combination 5, 0. Are you still able to see the screen there?
The screen's gone.
Okay, put this our combination in here. We get 5C0 gives us a value of 1. Okay, so this is essentially equal to the value of 1. 0.2 to the power of 0, that's also going to equal 1. Do I have that calculator here? Yeah, I do, yeah. So 0.2 to the power of 0 equals 1. Our combination, I should show it to you, I don't want to just make you assume. The combination was 5 and 0. There it is. That's also 1. Okay, great. And then 0.8 to the power of 5. 0.8 to the power of 5 gives us 0.32768. 0.32768. Oh, I think I memorized that. So essentially what they're saying is the probability of this is 32.7, no, too many decimals. I'll convert it after. 0.32768. And as a conversion, if you multiply this by essentially 100, what it's saying is there is a 32.768% chance of having 5 trials and no success rates. Okay? That's why our 0 was 1. So that's only one of them. We would then continue going with the probability of X when it's 1. Okay? And then we do the probability when it's 2. Probability when it's 3. Probability when it's 4. Probability when it's 5. Okay? Now obviously that would take a bit of time. So I actually built an Excel sheet, so I'm going to show you that right now. So So I've built our chart here. Here are n number of trials. So we have our, I shouldn't say n, actually that should be an x. Let's change that to x. Those are our success rates of our trials. So 0, 1, 2, 3, 4, 5. And then you can't quite see the formula. Actually, you can see it up here. Here's the combination. So 5 and A2 is 0. A3 is 1. So this is me going through the combinations with these different values in there. And this is kind of just showing it to you on the Excel. And this is telling us the probability of success here. This is the probability of failure. And this is the actual values we got in the end. So you remember when we had the value of 0, it's 0.32768. So there's a 32% chance that you would have no success rates. There's about a 41% chance that you'd have 1 success rate in 5 trials. And then you can see the probability starts to drop. To have 2 success rates is only about a 20% probability. To have 3 success rates, you have like a 5% probability. To have 4 out of 5 success rates, you'd have a 0.6. And to have all 5, the probability of all 5 of your trials being successful is 0.032. Okay, and the reason it drops so low is because remember our probability of success was only 20%. So if you're rolling a die, the probability of it landing on, let's say it's a 5-sided die, okay, landing on that one side 5 times in a row is very, very rare. Okay, and if you notice all of these probabilities, this is your distribution table, they add up to the value of 1, which makes sense. All of the probabilities should add up to 100%. So that's essentially encompassing all of the possible probabilities there are in this case.